You had two results in that Ohm's Law lab. Most of you plotted voltage along the x-axis, which makes sense for this first one. And current along the upper side, which makes sense because you more directly controlled the voltage in this experiment, and that's all good. And then you got a linear function, I hope. And so we know that in this case, y would be equal to some slope times x, or better yet, use the symbols for what we're actually using for x and y. Current, our y, is actually abbreviated with a y. We have our slope still, and then that's equal to voltage. And now we'd have a plus b term, intercept term. What did you guys find for your intercept? Where did that line go back and hit the y-axis? Better yet, let's just look at it. If you have 0 volts, how much current would you expect? 0. So while we might, if we mathematically plot out our formula, we might have a y-intercept on that. Physically speaking, we shouldn't. So a lot of times, especially in a lab situation like this, we're just going to ignore that because we know it physically shouldn't be there. And then the really interesting part comes in when you rearrange this, because Ohm's law usually is an I equals something times V. Instead, we'd solve for the V. So that becomes V equals, it'd be 1 over the slope of this times I.
What is I and M?
Current is I, M is a slope. Now that 1 over M should have significance in your experiment. I know you guys found it. I didn't look specifically at anyone else's. But if you take 1 over the slope of this, what do you get? You get your resistance. And typically speaking, this one goes actually very, very well. So it would be R times I. We usually write that in this form. This is the most common way to see it, V equals IR, but the order of those, of course, doesn't matter at all. The second experiment here, I asked you to hold the voltage steady, plot your, change the resistance, and plot the current. So we had resistance. Since we were changing that, I usually put that down on the x. That's measured in ohms. And then again, we had current. That resulted from that in amps. And the ones I saw, you had a shape something like that. Mm-hmm.
Doesn't matter how you make your graphs, because I know back.
It doesn't really. I mean, typically, yes. So the way these are, you can get the same results as long as you manipulate the relationship. That's okay. But typically, when you graph something, the thing that you change directly is going to be down on the bottom. The thing that you measured is going to be on the y. So we have independent variable, dependent variable. Ultimately, if you are okay with the math and you rearrange stuff, you're fine. You can it'll be the same relationship. Likewise here, this sort of form is a power function. So this would indicate that the current, our y, is equal to some number. I'll just put a little c. And it's almost an ohm. Times 1 over the resistance, most likely. So when you plot this, if you use your fancy calculators to plot these two, I would do a power regression. So that's, I think it's abbreviated either POW or PWR reg. And that's going to give you some terms. It'll give you the C term, and it'll give you what the exponent of resistance is. And so I checked out a couple people, and they got very close to the r to the negative 1, which is what this would be, and then you got this, a constant here. And this constant that you got should also have been fairly important for you. It's now appropriate to look at your lab sheets and comment. Yes?
You want me to tell you what we got?
Yeah.
Well, we originally got like 2.97, which is close to 3, which is the amount of voltage that we calculated.
It is. And it should turn out to be the amount of voltage. So that means this one becomes I equals a V over an R, which if we rearrange this and solve for V, again, is V equals I times R. That result is not by accident. That is the most important law in electronics, in electricity. It's Ohm's law. So make sure to note that somewhere prominent, because we will use it a lot when we're doing different circuits and circuit analysis. It relates the voltage either in a circuit or across a component, the current going through that component or the circuit, and the resistance of either that component or the whole circuit. The only important thing that you have to keep in mind, which we'll practice, is that if you're looking at one single component, say a resistor or a bulb or a motor, the voltage is just the voltage drop across that. So how much energy is lost by electrons going through. The current is just the amount of current going through that one component, and the resistance is just that one component. Or you can look at the whole circuit, and that works too. The total voltage supplied by a battery, say. The total current coming out of the battery, and then the total resistance that it senses in the circuit out there. Yeah, Elsa.
Just roll up the red and see it.
The V and the I we talked about a bit, and we have a pretty good basis for knowing what they are. This is the amount of energy per charge in this, so it's how hard are electrons being pushed through. This is the current, so it's how many electrons are going through, or how quickly. But this resistance, the opposition to the flow of electricity, is harder for us to grasp. We don't have previous units that can really help us. Certainly, if we look at this and we say, okay, volt is a joule per coulomb, an amp is a coulomb per second, times whatever an ohm is. We can solve for ohms here by multiplying through, but that would work out to a joule second per coulomb squared is equal to an ohm, and that doesn't have much meaning to it. That is really hard to picture. So instead, I want to do an experiment now that will sort of help show where this comes from in a wire, a simulated wire using Play-Doh. So we've got the Play-Doh over here. There are two experiments that you'll do as part of this. When you take these out, they have been in here for a while, so if you get one that looks totally nasty, it's time to throw that one away. That one is moldy.
I know they do that.
Yeah. Well, actually, you know what? I'll take that out because it might just be. It looks. Now that I saw it going into the trash, and I will now dig into the trash to get it. It looks like it is the paper on it. Yeah, I don't think I want to remove that paper though. Sometimes I'd put damp paper around it to moisten it up, but if you forget the paper in there, then the whole thing gets moldy and it's really not worth saving. But there are lots of other tubs over there, so you can try your luck.
I call orange.
You're going to make wires out of these, and the way I want you to measure is actually different from what's in the lab, because I guess I didn't review that lab well enough before I printed it. It works better to use a multimeter in this lab and just have the multimeter measure resistance. So you'll pick the two ports appropriate, use some of the probe wires up on the left door, and then you can just take those probes, insert them into the Play-Doh wire you made, and measure the resistance between the 2 points. it's a lot easier than the Ohm's law method that is detailed in the lab. So don't use that. That's a good way to do it, but this way works a fair bit more smoothly. Yes, Matt.